Your LLM can return perfectly valid JSON that is still impossible, negative quantities, reverse dates, or conflicting fields. Pydantic field and model validators will reject those failures before downstream code sees them. You'll learn the shape of a workflow that checks generated records, returns focused repair feedback, and retries only the failed answer. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. LLM outputs often look fine at first glance. The JSON parses, types line up, but the semantics can still be wrong. An order line with QTY equals -2 is structurally valid, yet meaningless. A schedule with start after end is syntactically correct, but impossible. If those slip through, downstream reports and processes break in costly ways. Semantic validation sits between parsing and business logic. It keeps the shape checks, then applies human rules so your pipeline can accept, reject, or repair items with confidence. The basic approach is straightforward. First, validate the shape with a schema. Next, run rules that encode meaning. If a rule fails, return a precise error location. Then, ask the model or a repair routine to fix just that field. That minimizes wasted generation and keeps retries focused. The trade-off is a bit more upfront engineering. The payoff is lower token waste and clearer incident logs. We will build a small, stepwise demo. It starts with a bare Pydantic model that accepts a negative quantity. Then we add a field validator, then a model-level validator for date consistency. After that, we validate a batch and prepare a minimal retry plan. Finally, we repair a single failing item and revalidate. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start with a minimal example that shows shape validation passing a bad quantity. This snippet parses one LLM JSON string with Pydantic and exposes a schema-valid negative quantity. It shows a model called line, where SKU is required as a string and QTY is required as an integer, and then it calls model validate JSON to turn raw JSON into a Python object. Because there is no semantic rule yet, QTY equals -2 survives validation, and the printed object contains that negative value. The point you see is that typed parsing works, but it does not enforce business meaning. That visible bad value passing shape validation is what motivates the guardrail we add next. Now we add a targeted field check, so small mistakes fail early and clearly. This example adds a Pydantic field validator to reject a schema-valid but unsafe QT. The line model keeps the same fields, but we attach QTY positive, which runs when QTY is present. If QTY is 0 or negative, it raises value error, and Pydantic wraps that as a validation error. Catching the exception and inspecting e.errors 0 gives a structured path to the failing field and an error message you can feed back to the model or your incident log. The visible output names the exact rejected field and error text, which makes retries cheaper and focused on the single cause. Field checks are great, but some rules live between fields. Next, we check relationships after parsing. This code uses Pydantic model validator to reject a reverse date range after both dates are parsed into date objects. Field validators can check one slot at a time, but when the bug is that start and end disagree, you have to compare the finished fields. Window parses ISO date strings into date values first, and dates forward runs on the completed model to ensure start is not after end. Raising value error inside that check produces a validation error you already handle the same way. The visible output shows a clear blocked business rule, which is far more actionable than a generic invalid JSON message. Now we turn to batch handling and avoid rerunning the whole batch for one bad item. This snippet turns Pydantic validation errors into a minimal retry plan. Instead of rerunning every LLM output, we iterate a list of JSON strings and call line.modelValidateJSON for each entry. When a validation error appears, we record the failing index into retry IDs and pull the failing field from e.errors to build a compact feedback payload. Good items go straight into accepted results. The visible output shows only output 1 selected for retry, so you protect correct outputs and only ask for repairs where they matter. Finally, we close the loop with a repair and a recheck so nothing sneaks through. This example closes the loop by validating, repairing one failed output, and validating the repair before acceptance. In practice, the repair step would be another constrained model call that receives the failing field and context. Here, the demo edits the data locally so you can see the flow. The failing item goes through the accept validation error branch. We produce a focused fix and then run line.modelValidate again to ensure the repaired object passes the same guards. The visible output shows both outputs accepted and a computed total, which gives a concrete success signal for the whole workflow. If you map this toy example to a real system, think of an order ingestion route that receives LLM-generated catalogs. Run schema parse, field guards, and model guards in that order. Keep the retry payload small and include the exact field path from e.errors and the original surrounding item for context. That saves developer time and tokens in repair calls. It is semantic validation for schema valid JSON. Use it when LLM outputs must meet business rules, not just types. One caveat is upfront rules engineering. You must codify the constraints you care about. A good next step is to add a retry budget parameter and tune it. Limit how many times a single item is sent back for repair and log each failure reason. That single knob quickly improves cost and stability in real pipelines. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.